You may recall that when we started our unit on caching, we started with an exercise that talked about file system calls. So what I want to do here is actually talk about those file system calls in a little bit more detail and introduce you to what the operating system is at a high level and what it does for you and how we interact with it. So let's begin by talking about processor privilege levels. Every processor has at least two different privilege levels, usually called user and supervisor mode. And what those privilege levels tell you, or they enable programs running at those levels to actually execute different instructions at times. And so different software runs with different privilege levels. In particular, what we think of as applications or the programs you write or regular programs run in what's called user mode. The operating system, however, runs in supervisor or privileged mode, and it's allowed to do things that normal programs aren't allowed to do. Now, I say most processors have two levels. The Intel architecture actually has four levels. But for the purposes of our discussion, we're just going to focus on these two levels, one of which is normal and one of which is like superpowers. And the operating system is the software that runs its superpowers. So why might you want operating systems to have more power than regular programs? Well, the answer is that there are some things you wouldn't want regular programs to do, like, oh, I don't know, halt the processor, right? So imagine that we were all sharing the student machines and I could write a program that said halt the processor. That would probably make you sad if you were trying to get your, oh, I don't know, lab done for CS 313. So we prohibit user processes from issuing certain instructions, but some of those instructions are actually kind of handy. So one class of instructions that we don't let regular programs access are those that have to interact with actual devices like disk drives, right? So it would be bad if you could write a program that interacted directly with the disk and like scribble data all over it and trash my data. I would not like that. So in fact, we limit what regular processes can do, but at the same time, your process might want to read data from the disk. So the operating system is basically there to do things on your behalf. So when your program wants to read data from a device like a disk, it basically asks the operating system to do it for it. And that act of asking the operating system to do things is what we call system calls. So a system call is when a user process wants to do something, and it's actually something it should be allowed to do, but it has to ask the operating system to intervene on its behalf and perform the actual operation because the operation requires something that normal programs aren't allowed to do. And in this unit in particular, we're going to focus on those system calls that might require the operating system to talk to an actual disk drive. If you look at the man pages, the system calls are those calls that are all listed in section 2. So with that as background, let's look at what are the system calls that the operating system provides in particular for the file system. And I like to think of them as, this family of 4 calls called open, close, read, and write. There are in fact other calls. Seek is the one you might see more often, but once you understand these 4, I think all the other ones will pretty much make sense. So now, you've never written programs that had to do anything fancy. You just call functions. And in fact, all the system calls are wrapped in library calls that invoke those system calls. So when you call open, you're invoking a library function that will then call the open system call. And so these wrappers are all in libc. And then libc knows how to do the special incantation that says, excuse me, operating system, I need you to do something for me. So at a high level, what open does is it takes a path name, right? So a human readable name, and it returns to you this thing, which is an integer. And magically, that integer somehow represents the file. And in some sense, this whole unit is about how do you have like this integer that magically represents a whole file? So that's what open does. What close does is it takes that file descriptor and it cleans up. It cleans up all the resources it allocated. Well, what are those resources? We'll figure that out too. Read says, here's an object that represents a file, this file descriptor, and here's a buffer. Please go read some number of bytes from that object into the buffer. Conversely, write says, here's a buffer full of data. Please put it into my file. And some of the things that the operating system is going to do is say, well, you're asking to open a file. Is that one you're allowed to open? Is it one you're allowed to read? Is it one you're allowed to write? And so that kind of security enforcement is one of the reasons why we have to go through the operating system to do these things. So given this API, you could imagine writing a utility that copies data from one file to another. And in fact, that's what you're going to do in just a few minutes. And so to a first approximation, what we're going to do is we're going to open the file, one for writing, one for reading. So we're going to have one FD that represents a file that I'm reading from, and another FD that represents a file I'm writing to. And then I'm going to loop. And while there's data left to read, and in a moment you'll know how to figure that out, I'm going to read data, and then I'm going to write it to the new file. And then when I'm done, I'm going to close both of those files. So let's look at those system calls in a little more detail. So I said that open takes a path name. Notice that it's a constant because you don't have to change that path name. It's like, here's the file I want to open. It takes some flags that describe the modes in which you want to open it. And then it takes something called a mode, which only kicks in if you're creating the file. And we'll talk about that in a whole other slide. So these flags can tell you lots of different things. So one, they can tell you like, are you allowed to read only? Are you allowed to write, or are you doing read-write? So you can open files in different access modes. They also tell you what to do, like if the file doesn't exist. And so there are flags that say if it doesn't exist, you're allowed to create it. Oh, exclusive says you're only allowed to create it if no one else is doing that at the same time. And this is how we resolve the race condition between checking to see if a file exists and trying to open it and create it. And then we've learned all about caching in hardware. And I said that there's caching in software. And the file system is one of the biggest users of caching, but there are flags you could say at open time that might disable caching. Say, for some reason, I don't want you to cache. And you might think about like, when would I not want the file system to cache? And that's an interesting question to ponder. And then finally, this mode says, I'm going to create a file. Who's allowed to access that file? And so that's what the mode is going to tell us. So here's an example how we use open, and you will get to write your own open calls in just a few minutes. So I promised a digression on mode. So here is the long form output of ls on some files in my home directory. And you may have done this command before, maybe you haven't. But if you look over at this side, there's this gobbledygook of characters. And what that gobbledygook is really telling you is who has permission to do what with these objects. And so these objects are represented as 10 characters, and each of those characters actually corresponds to a bit. All right. So the way this works is that you have the type, I'm sorry, I misspoke. The type is actually more than one bit. So the type says, what kind of thing is this? And the kinds of things you might have are like regular files. So foo here is a regular file, so it just has a dash. Some of the files are directories or folders. That's where you see the D. Sometimes you might see L for a symbolic link. So the type tells you what kind of object it is. The rest of these are broken into 3 sets of 3 bits. And they correspond to the owner of the file, that is the person creating it. The group, which is the group to which that user belongs when they're creating the file, and you can belong to multiple groups. And then there's the rest of the world, so everybody else. And then within each of these sets of 3 bits, we have 3 possible permissions: read, write, and execute. So the read bit obviously says you can read it, write says you can write it, X says you're allowed to execute it. Well, what does that mean? Well, when you build a program and you get a program that in theory is allowed to run, it gets the execute bit set. Also, in order to traverse a directory or go into a folder and examine its contents, you have to be able to execute that directory object. So if we look here, so dot is my home directory. And what you see is that the little D bit is set to, yay, it's my directory. And then the permissions associated with that is that I, as the owner, can both read and write and execute. But nobody else, even if they're in my group or the rest of the world can do anything with it. And so that's how we lock down our directories to make sure that nobody can snoop in our data. And in fact, a CS 313 student was on the student machines and noticed that they could see all the other accounts on the system. And in some cases, they could actually see the files in those accounts. And rather than snooping, they immediately reported it. And I talked with the folks in IT. And there's two things. So one, when you get an account on those machines, you were told, oh, by the way, you can see all the other accounts which are indexed by CWL, and you are agreeing that people can see your CWL and that you will not do anything with anyone else's CWL. But I said, you know, students don't necessarily know about these permissions, particularly before they've taken 313, and they may inadvertently change those permissions to be something that allows other people to see their files. And so now there's a check that runs every night to make sure that people haven't left their directories open when they didn't intend to. So that mode argument to open, bringing this full circle, lets you specify what permissions you want to assign to a file if you are in fact creating it. And the way we typically write those is that since we have 3 bits for each of the modes, that corresponds to 1 octal digit, right? So hex is base 16, octal is base 8. And so you specify the octal digit that corresponds to each of these permissions. So if I want to open a file, and this is another case where like knowing your binary to octal conversion is really handy, right? What you learned is that, oh, read-only access is 400, right? Because I have a 1 in the read bit and 2 zeros, right? Read-write access, that's 6, right? A 1 here and a 1 here. And read-write and execute is 7, 1, 1, 1. So you can experiment with that. Now let's go on to close, which is perhaps my favorite because it's the simplest of the calls, but you should always close your files. So close takes the FD of an open file, and it basically frees up all the resources that the operating system allocated on your behalf when you opened the file. And so close should return a 0 on success or a -1 on error. And file system operations are one of those sets of operations that you really, really, really want to check return codes. One of the largest sources of bugs in programs is people not checking return codes. Now let's look at read and write. So both of them will have roughly the same structure. They're going to take a file descriptor, and then they're going to take a buffer. So this is an address that corresponds to a bunch of data and a number of bytes. So in the case of read, what we're doing is we're saying, operating system, find the file that is represented by this file descriptor, read this many bytes into this buffer. At the end, I would like you to tell me how many bytes you read. If we were at the end of the file, you couldn't read any bytes, so you will return a 0, which tells me I'm at the end of the file. If you read some bytes successfully, you will tell me exactly how many you read. And in general, I want that the number of bytes read corresponds to the number of bytes I told you to read. But I should check that. Because let's imagine that I have a file that's 1 byte long, but you don't know that. So you open it up and you say, read 1,000 bytes. Well, I can't read 1,000 bytes. I don't have 1,000 bytes. So I'm going to read 1 byte, and I'm going to return a 1 to you that says, I read 1 byte. And you say, oh, I guess that means there's no more bytes in the file. So I return the number of bytes, and if something bad happens, I return a -1. So in this case, I'm going to allocate a buffer that has 4,096 bytes. And I'm going to ask read to go to some FD that I've already opened, and into this buffer, read 4K bytes. And 4K is a common number when we call read, because read and write are file system operations. They are talking to things that talk to disks. And we typically access things in big chunks because the disk is really slow. We don't have to, but I hope as you remember from earlier in the semester, the overhead of going to the operating system over and over and over again to ask for like 1 byte is really high. And so we tend to want to amortize this cost over large buffers. Now that you've seen read, I'm hoping you can guess what write looks like. So here's write. The prototype is almost exactly the same. In fact, it is exactly the same, except the semantics are that please read this many bytes. I'm sorry, please write this many bytes from the buffer into the file. Now, one question you might be asking is like, well, where do you read these bytes? Do you read them or write them from the beginning or the end? And this is where we get into the concept of like, what do file descriptors keep track of? So Unix and Linux-like systems implement what's called a byte stream model of files. So the mental model that they want you to have of a file is that it's just some stream of bytes. And the file system actually keeps track of that for you. So when you open a file, you are set at the very beginning of the file, byte 0. And as you read, however many bytes you read, that's how much it advances sort of this pointer that keeps track of where you're reading or writing. And so the offset at which you are reading and writing is implied in the read and write call. And I mentioned earlier that fseek call, that's the only way that you can change the position of where you're in the file. Otherwise, the assumption is that you're reading sequentially, you start at the beginning, and you just keep reading or writing bytes. All right, so hopefully that'll give you a little background that'll prepare you for class. See you soon.